A simple shift in light control could revolutionize quantum computing. Scientists have discovered a clever new way to control the light emitted by quantum dots, tiny crystals that can release individual photons. These findings could transform how we build quantum technologies, from ultra-secure communication systems to experiments probing the mysteries of quantum physics. The challenge of single-photon sources. Quantum dots are tiny semiconductor structures that can emit single photons when triggered. However, each dot is unique, emitting light at slightly different wavelengths. This variability makes it hard to combine multiple dots for multi-photon experiments. To overcome this, researchers typically use a single dot and split its light into different spatial and temporal modes using a fast electro-optic modulator. But these modulators are costly, require custom designs, and can cause energy losses, limiting their practicality. An elegant optical solution emerges. A groundbreaking study led by Vikas Ramesh of the Photonics group at the University of Innsbruck, alongside collaborators from Cambridge, Linz, and other institutions, has developed a novel approach. Their method uses a technique called stimulated two-photon excitation, which allows quantum dots to emit photons in distinct polarization states without needing electronic switching. In tests, the team successfully generated high-quality two-photon states while maintaining the purity of single-photon emissions. How the technique works in practice. The process begins by exciting the quantum dot with precisely timed laser pulses to create a bi-exciton state. Then, polarization-controlled pulses trigger photon emission in the desired direction. As lead researcher Vikas Ramesh notes, this approach moves the complexity from expensive electronic components after photon emission to the optical excitation stage, marking a major step toward practical quantum dot sources. The study's first authors, Yusuf Karli and Iker Avila Arenas, described the experience of working in the Photonics group during their master's thesis as fantastic, highlighting their involvement in the Erasmus Mundus Joint Master's Program. Moving complexity to the optical stage. By shifting complexity to the optical stage, the method eliminates the need for costly electronic hardware. This shift is critical for real-world applications, as quantum dot sources must be reliable and efficient. As Ramesh explains, we've moved the complexity from after photon emission to the excitation stage. This is a significant leap forward in making quantum dots viable for practical use. The research envisions expanding the technique to generate photons with arbitrary linear polarization states using engineered quantum dots. Real-world quantum applications. The study's implications are vast. Gregor Ways, head of the Photonics Research Group in Innsbruck, highlights applications in secure quantum key distribution, where multiple photon streams can enable simultaneous communication with different parties, and in multi-photon interference experiments that test the foundations of quantum mechanics. Collaborative breakthrough. Published in NPJ Quantum Information, the work represents a collaborative effort spanning quantum optics, semiconductor physics, and photonic engineering. Supported by the Austrian Science Fund, FWF, the Austrian Research Promotion Agency, FFG, and EU programs, this research underscores the power of interdisciplinary innovation. Controversy, future questions. But here's where it gets controversial. While the new method reduces reliance on expensive electronics, some experts argue that it may not fully address all challenges in quantum dot stability or scalability. As the study's authors note, this is just the beginning. There's still much to explore. Will this approach truly revolutionize quantum computing, or will it spark debates about the future of quantum technology?